Hello. So we're gonna do some related rate of changes, calculus and differentiation. If you've made it this far, and I'm gonna be using some questions from this book right here, and if you have it, you can tag along. You can go to page 533, and these ones will be doing 3 questions. We have page 534 here as well, so you can be doing this along with it. I'm just doing this just because it's actually quite was quite complicated when I learned it in class, and I feel like I might forget it. So, okay. So, a 5-meter long ladder rests against a vertical wall with its feet on horizontal ground. The feet on the ground slip, and at the instant when they are 3 meters from the wall, they are moving at 10 meters per second. At what speed is the other end of the ladder moving at this instant? All right. So always with these questions, it's really helpful to draw out a diagram. I'm going to draw a diagram right now. This is the 2 ends of the ladder. This is the wall, and this is the floor. The ladder is 5 meters. And let's call the y distance here y, and the x distance here x. All right. Now we always with these questions we want an equation that relates these two variables x and y, the two different rates of change, and so we want, and this is a right angle triangle, so we're going to use Pythagoras. X squared plus y squared, and remember this is equal to 5 squared, and that's equal to 25. Okay. Now what the rates of change are always based on time, right? So what is the change in x every second? What is the change in y every second? And so we're going to have to use implicit differentiation, and we're going to have to differentiate everything with respect to t, t being time. But let's see. So when let's write down the information first. So when x is equal to 3, so when x is 3 meters from, so when x is 3 meters, dx over dt, so dx over dy, dx over dt, differentiation of x with respect to t is, as it says right here, 10 meters per second. And so that would be 10. So x, this is meters per second. Okay, does that make sense? So when x is at 3 meters, the differentiation of x with respect to t is 10. And because t is time, it's 10 meters per second. Now we have to use implicit differentiation to differentiate everything here with respect to t. And I'll walk you through it if you don't remember what implicit differentiation is. So the differentiating x squared with respect to t. So actually I'll just do this. So we're going to do 2x times dx over dt. And the reason for this, if you don't know, is because it's something related to the chain rule. So you have to, like, let's say like we all know the example of the chain rule, right? So let's say fx is equal to gx gu, right? So it's two different things, and then u is, I don't know how to explain this. Basically x, the variable x, contains within it relation to t, and because we have no t here, we're differentiating in relation to x, we have to use the chain rule. So we move the power to the front. So move the power to the front. That's 2x, right? Just like how we did here. And then you have to times by the differentiation within the variable, within what you're differentiating. So that's so that would be dx over dt, like differentiation of the x itself over dt, if that makes sense. Hopefully it does. So okay, So we've differentiated x squared with respect to time. We'll also differentiate y squared with respect to time, which will turn out to be 2y times dy over dt, and then differentiating 25 with respect to time, because 25 is a constant, it will turn out to be 0. Okay. So now, so it's asking for what the speed is the top end right here, the n related to y, moving at the instant when x is 3. So we want to know what dy over dt is when x is 3. And we want to know what y is. So we know what dx over dt is because dx over dt is here. We know what x is because we know x equals 3. We want to find dy over dt, so that leaves us the two unknown variables of these. And we need to figure out what y is to find out what dy over dt is. So using Pythagoras, again, it's 5 meters here, it's 3 here. And so this length y has to be equal to the square root of 25 minus 9, which is equal to square root of 16, which is equal to 4. And so y equals 4. When x equals 3, y equals 4. And so if we substitute our values in here, x is equal to 3, so that's 2 times 3 times the differentiation of x over dt with respect to t at x equals 3, which is 10 meters per second, plus 2 times y when x equals 3, which is 4 meters, times dy over dt equals 0. I should have rearranged the equation first. I'm going to do it right now. So dy over dt is equal to minus, that looks like 60 over 8, which is equal to, let's just do it over here, minus 60 over 8, minus 7.5. So when x is equal to 3, dy over dt is minus 7.5 meters per second. All right, so that's the answer for the first question. All right, so now we're going to move on to this question, the second question, and this is on page 534 if you want to tag along. All right, a square has side lengths x centimeters and area a centimeters squared. The side length of the square is increasing at 2 centimeters per second. State the relationship between a and x. So it's a square, and so the area is just the square of the lengths. With b, differentiate the relationship in a with respect to t. So again, we do the same thing as last time. It's implicit differentiation. So it's dA over dt is equal to 2x dx over dt. And see, at what rate is the area increasing when the side length is 6 centimeters? The rate at which the area is increasing is dA over dt, and the lengths are side 6 centimeters. And we know that the change in the side lengths are 2 centimeters per second, and it's constant. And so we can simply substitute everything. This one is 6 centimeters times by 2 centimeters per second gives us, it looks like 24 centimeters squared per second. Okay, let me just check. 2x276. Okay, yeah, that looks right. So 24 centimeters squared per second. All right, moving on to the next one. Air is pumped into a spherical weather balloon at a constant rate of 6 pi meters cubed per minute. Find the rate of change in the balloon's radius at the instant when the radius is 2 meters. Okay, so let's imagine a sphere with a tube coming into it, with air blowing into it. So every minute there is 6 pi meters cubed of air going into the balloon. So that's contributing to its volume. And then we have, from this center point here, we have the radius. Let me just redo that. Okay. So we need to, again, relate the volume to the radius. So volume is equal, of a sphere is equal to 4 pi over 3. 4 pi over 3 times r cubed. Okay. And then we're trying to find the rate of change in the balloon's radius. So let's differentiate everything with respect to t. So that would be dv over dt is equal to 4 pi. So we times the 3 over, so that would cancel out with this 3, right? So it'll be just 4 pi times with r squared times with dr over dt. And we're trying to find, so let's isolate this, let's rearrange this. So dr over dt is equal to dv over dt divided by 4 pi times r squared. So dv over dt, the rate of change in volume is the 6 pi meters cubed. Every minute, the 6 pi meters cubed of air is being pumped into the balloon. And so the volume of the balloon is increasing by 6 pi meters cubed every minute. And so that would be here, 6 pi meters cubed on the top. 4 pi, and then the r squared. So at the instant when the radius is 2. So we know that r is 2 right now. And so the equation right here will be 4 pi times 2 squared. So let's just type this in here. 6 pi divided by 4 pi times 2 squared. And it gives us this one right here. It's not giving us a nice fraction, so let's do this by hand real quick. 6 over 4 times that. So 6 over 16 is equal to 3 over 8, and that itself is equal to 0.375 meters, and this is the dr over dt, the change in radius. So that's meters every minute. And so what this means is with 6 pi meters cubed of air being pumped in every minute, the radius of the sphere is changing. It's increasing by 0.375 meters every minute. But yeah, these are the easy type questions of related rates of change. Thanks for watching, and hopefully that made it more clear how it all works.